Unit 17, Forecast and Warning Process. In this unit, we'll identify the federal and local agencies responsible for hazardous weather forecasts and warnings, understand the concept of uncertainty and probabilistic weather forecasts. We'll understand the weather forecast process and describe the methods by which hazardous weather warnings can be delivered. And this is a unit that I think will be very relevant for emergency managers. This is the space in which you live in terms of what you have to do with when receiving weather information and making decisions based off of that. As we know, weather is a global problem. This is not something that exists within the boundaries of just one nation. And so regional specialized meteorological centers, in the case of tropical cyclones, have been designated by the United Nations, and they're illustrated in this figure. The National Hurricane Center is the RSMC, located in Miami, Florida. Their domain is the North Atlantic Ocean and the Northeast Pacific. The Central Pacific Hurricane Center, located in Honolulu, Hawaii, is in charge of tropical cyclone forecasts everywhere from 140 degrees west longitude to the dateline. So anytime a tropical cyclone enters that jurisdiction, there's a handoff from Miami to Honolulu. For the rest of the world, the nations in charge of the forecast of tropical cyclones for that jurisdiction depend on United Nations designations. Tokyo, the Japanese Meteorological Agency, is in charge of the typhoons in that area. Officially for civilian populations, New Delhi in India, La Réunion for the southwest Indian Ocean, and then Australia for the waters surrounding there, etc. However, the United States Joint Typhoon Warning Center was also established as a way to advise U.S. government interests in those areas. So their domain is large, consisting of the entire southern hemisphere, the Northwest Pacific, and the northern Indian Ocean. The National Weather Service is the U.S. Civilian authority for weather forecasts and warnings. There are 122 local weather forecast offices, and then 9 national centers. Those include National Hurricane Center, Weather Prediction Center, Climate Prediction Center, Storm Prediction Center. The list goes on. The Storm Prediction Center is in charge of convective outlooks and tornado watches, severe thunderstorm watches, etc. The National Hurricane Center, of course, is focused on the hurricane threat. So we'll start there. National Hurricane Center is located in Miami, Florida. Their area of responsibility is the Northern Atlantic and the Eastern North Pacific tropical forecasting domain. They only issue forecasts and advisories tropical cyclones while over water or shortly after landfall. So what that means is inland tropical cyclone threats depend on forecasts and warnings from the local WFOs, the Weather Forecast Offices, as well as the Weather Prediction Center located in Maryland. They work closely with the National Hurricane Center on defining the threats associated with the landfalling tropical cyclone. The Weather Prediction Center was formerly known as the Hydrometeorological Prediction Center because they focus on the water-related hazards associated with precipitation, so flooding, heavy rain. These are the types of forecasts they focus on. They're responsible for precipitation and medium-range forecasts. And so, of course, you can see how this would be a collaborative effort with the National Hurricane Center whenever a hurricane is making landfall. They issue advisories for post-landfall tropical depressions. So again, that's where the handoff occurs after a tropical depression has been downgraded and the storm is inland. They're co-located with the Environmental Modeling Center and the Climate Prediction Center, also members of NCEP. The Climate Prediction Center is responsible for operational forecasts of climate variability. So if you remember, at the beginning of the weather section of this course, we showed the weather and climate spectrum. So the Climate Prediction Center is focused more on the upper right part of that chart. They're looking at the longer scale, longer time scale, larger spatial scale events, such as drought, above and below average temperatures for a certain part of the country. They issue weekly to monthly forecasts of temperature and precipitation. They'll also do outlooks for drought, as well as hurricanes or the development of tropical storms. So there's a global sort of tropical hazards outlook as well, included in one of their figures. The Storm Prediction Center is located in Norman, Oklahoma. They are in charge, they're the national center in charge for severe and fire weather forecasts for the for the CONUS, for the contiguous United States. They are located in Norman because they are right in the heart of quote-unquote Tornado Alley, and they have a lot of expertise co-located with the University of Oklahoma, with the National Severe Storms Laboratory, in developing better techniques to forecast these types of events. Severe thunderstorms and tornadoes can be categorized as convective events because they're based on the convective instabilities we talked about earlier in the course. SPC is also the ones issuing convective outlooks and severe thunderstorm and tornado watches. They coordinate, of course, with the local WFOs whenever they issue these watches, so that whenever there's a threat, it's properly outlined. Space Weather Prediction Center is another national center located in Boulder, Colorado. They monitor solar activity, and they're responsible for space weather alerts, watches, and warnings. Again, the public doesn't quite hear about space weather as much as other types of hazardous weather, but this is, of course, as we mentioned before, a concern to the telecommunications and energy industry, of which we all depend. River forecast centers. These are a way within the National Weather Service to better predict and to operate on water hazards that occur from really heavy rainfall. And so these are based on watersheds, of course. And so you see that they don't follow state boundaries necessarily, but they follow the basins such as Missouri River, the lower Mississippi River, etc. The 122 WFOs can be seen here in this map. Notice how all the county warning areas, the CWAs, are different shapes and sizes. Albuquerque is very large. It covers most of New Mexico. Then you have the smaller ones, such as Melbourne, Florida, New York City. As you can probably imagine, these are based in part due to population density. So the county warning area is the jurisdiction in which a WFO will issue severe thunderstorm warnings, tornado warnings, flash flood warnings. This is their warning jurisdiction. And of course, they coordinate with their neighboring CWAs so that their forecasts are consistent, but their specialty is in that CWA. The forecast process, in general, if you were to put yourselves in the shoes of a meteorologist for a moment, is as follows. When you start a shift, you would want to, before you even start forecasting the future of events, you want to know what has already happened and what is currently happening. And to do that, you would want to analyze trends in satellite radar, surface upper air observations, or using all the technologies we've already discussed to understand how the weather is changing. And then you want to forecast, or you want to follow the forecast funnel. And what that means is you would spend some time looking at the large scale conditions around the globe, seeing what happens in Japan could potentially affect what happens on the west coast of the US later that same week or the week after. So it's good to see a global scale, to get a global understanding of the weather events as they occur. And then you work your way down, you look at the synoptic scale, you look at what's happening across half the country. Then you go down to the mesoscale where you look at what's happening in your local area. And that's how you drill down to the local impacts. Then to predict the future, you'll want to evaluate the numerical model output, of course. You want to look at computer models, look at the ensembles, see what the uncertainty is right now for a particular scenario, especially if there's a storm threatening. And then the forecaster has to make decisions based on available data. So an important thing to remember is that forecasting isn't purely a science that then the decision maker has to extract information from. The forecaster itself is already, himself or herself is already a decision maker. And so what that means is, in order to distill the uncertainty behind the science, the forecaster has to make a decision on whether to issue a forecast a certain way or to issue a watch or a warning. And this already introduces a human aspect to the process, which then the decision maker, such as all of you as emergency managers and first responders, will have to act upon. A forecaster has to issue routine products at fixed times throughout the day. This is very different from the research community. In the research community, when you ask a question, you will take as long as you need to, as many years as you need to answer that question properly. For a forecaster, there are certain times throughout the day when he or she has to issue a forecast. So that means regardless of whether you're right or wrong, or whether you feel comfortable with your forecast, you still have to issue it by that time, because consistency is key when it comes to operational information. For a decision maker, it's important to know that at a certain time of day, an update to a forecast will be available. And so forecasters operate under a time constraint. They issue warnings as necessary, but they're under time constraints for routine products. And so this is important to consider, particularly when on the receiving end of forecasts. Forecast uncertainties, it's a challenge. Sometimes outlooks or watches are issued, but nothing happens. And conversely, nothing is forecast, but tornadoes can still occur. This is a really classic struggle among the weather forecast community. And depending on which side we fall on, we could either be contributing to misses or false alarms. And so we'll talk about that here in the following bullet. Probabilities can be helpful, but people still need to make decisions. There's a trend within the meteorological community to move into the realm of probabilistic forecasting. And what that means is there's an effort to try to communicate a forecast based more on a range of possibilities instead of just giving one number. So someday in the future, rather than saying a high of 76 and a low of 65, you may hear a forecast that consists of an 80% chance of a certain range of temperatures. Social science supports that probabilities are digestible by the general public, but how it's communicated is something that's still, of course, a big question. When we talk about probabilities as a decision maker, oftentimes we still have to make decisions as a go or no go. It's still a binary yes or no, even though you're presented with probabilistic information. So this is a challenge that will be growing into the future as probabilistic forecasting gains traction in the meteorology community. So of course, meteorologists have to weigh misses against false alarms. What that means is a miss would be not forecasting an event to occur, but it actually occurs, versus a false alarm, where an event doesn't occur even though it was forecast to occur. Which situation, if you're a meteorologist, would you prefer? Of course, false alarms are preferred. But a big drawback to high false alarms, of course, is public complacency. It can lead to the cry wolf scenario, where the public may lose trust in a forecast, and that could impact public safety later on down the line. So a meteorologist's task is always to try to reduce both misses and false alarms. But to do so perfectly, of course, is an impossibility. But it's a constant effort to try to improve upon. Oftentimes in the planning world, we think about return periods. We hear about a 100-year storm, for example. What does that mean? A return period is expressed as the recurrence interval of a particular event. So it is an expression of probability. That doesn't mean a 100-year storm will occur once every 100 years. That means that in any given year, there is a 1 in 100 chance that that type of storm of that magnitude may occur. And so you can think of the return interval as the number of years divided by the number of occurrences. So it's a probability, an annual probability of at least an event of that magnitude. And again, 100-year event does not necessarily imply that it will occur every 100 years. Now, speaking of planning and structural and engineering considerations, we want to consider cumulative probabilities over multiple years, right, in terms of probability of a failure of a structure, given a cumulative range of events throughout multiple years. And this is more mathematical, and this is something that structural engineers have to strongly consider. When we talk about the interface between science and decision-making, we have to consider what's called the weather enterprise. This is the entire field that includes researchers, operational forecasters, as well as those who are focused on societal applications of meteorology. The research is, of course, the area that includes academia, that includes the government research labs, where meteorologists are attempting to come up with new techniques and tools to be able to enable better forecasting. The operational world includes the National Weather Service, the private sector, forecasters who have to monitor the current weather, and they're issuing the routine products that then the decision makers will use to inform their decisions. Societal applications, of course, is the space where we all fall under. as emergency managers and as responders and planners, we have to take not just the existing forecasts that are being disseminated by our forecast centers, but also research, the latest in research, to apply to the problems that we're facing on a daily basis in society. And so the key thing here with the weather enterprise is that this has to be balanced. There has to be discussions and communication ongoing between all three sectors. Otherwise, this enterprise breaks down. And unfortunately, this has occurred a few times in history. But overall, we want to make sure that as society, as those focus on societal applications, we want to be communicating with researchers and operational meteorologists. Those in operations would want to make better forecasts informed through the latest research techniques as well as through the needs of those under the societal field. This is important to know when we're considering our sources of forecast. So television broadcasters are very, very important. They're the public face of meteorologists during hazardous weather. They disseminate a lot of the National Weather Service warnings. The National Weather Service is the only official source for the watches and warnings, so therefore these are being disseminated. However, often broadcast meteorologists will add value to that by including their own forecasts, their own opinions on what the conditions may be in their local viewing area. The vast majority of the public actually uses the media as the primary means in which they get weather forecasts. Very few actually will go directly to a National Weather Service website and read the material. But as decision makers and emergency managers, we have to be able to do both, to be able to weigh both and understand the interface between the two. There are multiple national and local TV news stations. On the national level, we have stations such as the Weather Channel. They're based in Atlanta, but they don't have any local offices. Local news stations can drill down a little more specifically to a local area to be able to inform the viewers in that area if there's any severe weather that threatens. Similar to National Weather Service offices that are broken up into county warning areas of jurisdiction under the weather forecast offices. The TV broadcasters also relay and interpret watches, advisories, and warnings, and other government officials. So press conferences during a major weather event. These are all things that you can get through local media. There are other ways to disseminate weather information. Of course, there are outdoor warning devices, and many of us here in this room are probably very familiar with this already. They're essentially World War II, Cold War air raid sirens adapted for weather purposes. It really depends on the jurisdiction. And this is the take-home point here, is that depending on the county, there are different policies for when outdoor warning sirens are used. And this should be familiar to, this problem should be familiar to everyone here in this course. But this is a reminder that on the local level, the public may not necessarily be aware of the policy for that jurisdiction, particularly in areas with a lot of tourism and areas that may have a transient population. These sirens are only intended to be heard when outdoors. They should not be the only source of information because it's not specific enough. Again, some counties may be using them for tornadoes as well as severe thunderstorm winds, and some even use them for fires. So this is a very important consideration when acknowledging the utility of these devices. NOAA All Hazards Radio is actually a really nice tool. They can be set on alert to wake up whenever there's a warning that's issued for your particular county. These do not follow the polygons that are currently being used to indicate severe thunderstorm and tornado warnings. They're still by county, but at least you can specify which county you would like to receive warnings for. Nowadays, of course, social and wireless media is becoming more and more popular as a way to reach people when it comes to hazardous weather. Facebook and Twitter are now being used regularly by Weather Service forecast offices around the country. They can also be used by the public to request assistance. And this is something that actually contributed to dialogue between, say, FEMA and residents along the northeast coastline that were impacted by Sandy. Wireless emergency alerts are another system where cell phone towers and also can actually be used to indicate a person's cell phone location, and then alerts are pushed through the WIA mechanism to inform a user in that location that there's a warning issued for that area. They're 90 characters long, advising to seek more information or shelter for imminent danger, as in the case of tornadoes. They're for all hazards. There are also Amber Alerts that can be disseminated through there, and presidential messages. Those are the only ones that cannot be turned off, even though the system itself is an opt-out system. There's a FEMA app with crowdsourcing that is available, and this slide is outdated the moment we use it, because on any given day there will be more and more apps being developed to apply weather for the benefit of the population. So I'd encourage everyone to go through their app store and explore some of the various weather apps that are out there. Some are marketed by the private sector, some are available from federal agencies such as FEMA, and then some are from nonprofits such as the Red Cross. They can all be very useful in different situations. The Red Cross app has different types of hazards in there, along with advice for preparedness. So again, I would encourage everyone to explore available apps. This unit concludes with a severe weather forecasting activity where we'll actually explore the sources for information that are online. This activity will depend on what's going on in the current weather, so you'll get a real-time look at how you can explore the current conditions around the country.